I'll go back to here. I mentioned granulites being very high temperature and pretty high pressure too. It's sort of uh, this facies, so granulite facies, is fairly high grade, and it's also typically anhydrous, so no hydrous minerals whatsoever. So that means no amphiboles, no muscovite, no biotite, nothing like that. Um, it is mostly pyroxene and plagioclase. So the black mineral being the pyroxene and the white mineral being plagioclase. No quartz either. This one happens to be foliated. They don't have to be foliated. You might see a granulite facies nice like this, or it could be a non-foliated granulite. And then I suppose in that case you would simply call it a granulite. All right, just to continue with the non-foliated rocks, I mentioned blue schist and eclogite before. Blue schist is a bluish, and I think you will agree that's bluish, metamorphic rock that is subjected to like subduction zone metamorphism, so high pressures and low temperatures. It commonly has this blue sodic amphibole. There's some green pyroxenes and red garnets. That's pretty typical assemblage of minerals. There's probably also muscovite in there. Um, you can call this is non-foliated. You could have a foliated blue schist too, and in that case, it would actually be schistose, right? It would be a schist, and it happens to be a blue schist, facies schist. But if it's just a like a gabbro or a basalt protolith, an igneous protolith, I would guess that oftentimes you end up with a non-foliated rock. Although I did describe to you a gneiss that I saw. It was in the southern Ural Mountains in Russia during my PhD, where I saw the blue, green, and red banded gneiss. That's pretty cool. There's a lot of eclogite and blue schist. So it could show up as a foliated rock too. But in that case, it would have been a blue schist facies gneiss that I would have called it. An eclogite, I said, was the Christmas rock, red and green. So red garnets, this is loaded with garnet, and green pyroxenes. Um, but again, this is you can name a non-foliated rock that has a mafic protolith, a gabbro or basalt, as just eclogite. This is eclogite. But you could also have an eclogite facies schist or an eclogite facies gneiss, like I just mentioned. So they could be foliated, but in this case, we're using the name to actually the name of the facies to actually name the rock. So blue schist and eclogite. Let's skip forward to here. I've talked about migmatites, and I showed you one migmatite already. You're ready to see another migmatite. It's a heterogeneous rock, right? It's a mixture of metamorphic rock, the dark gneiss in this case, and new igneous rock, so the melt phase. So these light bands in here are actually, these are called leucosomes. These are the little light colored blobs of melt that are, or stringers of melt that are strung out in the foliation. This is all folded together as well. So the foliation bends around like this. But in this case, the melt has largely stayed within the foliation plane, actually. But this is coexisting igneous and metamorphic rock. So the metamorphic rock, well, yes, it is, because the dark part, it's given the name melanosome, just like melanin. It's a dark. I think that's where the word comes from. So this dark is piece of metamorphic rock, or the dark gneiss, is what is left after you extract the quartz and the feldspar. And right, that's what you would expect. You would expect the lower temperature minerals on Bowen's reaction series to melt first as you increase temperature. So when these reach that melting, those melting conditions, it's just the quartz, the feldspar, maybe some muscovite that goes into the melt, that is melted and removed from the rock, right? So it's actually separated, even though it's still here in the migmatite, but it's separated from the metamorphic rock. So we have igneous rock that's now crystallized within metamorphic rock. Hopefully that's clear. Um, this is at the intersection. This is where metamorphic processes and igneous processes meet. This is where they are coexisting at the same pressure temperature conditions, but the melt doesn't interact with the remaining metamorphic rock any longer. The melt then becomes igneous. It undergoes igneous processes. So in this case, the melt crystallized in place. So these are pieces of igneous rock, and the black part are pieces of metamorphic rock. I think I just repeated myself, but it's probably helpful to say it a couple different ways. Okay, so that's at that at those boundary conditions. Wrong slide. Okay, and so I worked on this origin. We've got the Sierra Nevada here on our coast, and that's part of the Cordillera that goes all the way up into Alaska, and even there's Cordilleran type tectonic activity or rocks left behind and processes that they experienced all the way down into South America. So the Chilean arc and Peruvian arcs are part of this. You can see the old collision zone from Pangaea. This western Norway is part of it, eastern Greenland, the eastern part of the U.S., northwestern Africa. They don't show any along eastern Brazil and Argentina or western Africa. That's a pity. It could just be that somehow those rocks aren't preserved from the collision. What's my point of this? That's where those mountain belts are, where the crust is thicker, much thicker than the shields and the platforms. So that's where you expect to find deformed rocks, metamorphosed rocks, volcanic rocks, plutonic rocks, because that's in the collision zones. That's where we've got magmas being produced and volcanoes erupting, where the crust is thickened and we have metamorphism taking place at high pressures and temperatures deep in the crust, in the middle and lower crust. That's where all the action happens. That's where the rocks are really interesting to me. I think I'll stop there. That pretty much covers it. I just wanted you to point that out so that you could see just how many places on Earth you would expect to find all these rocks that we've been talking about. Okay, finally, what you learned in this lecture. This is the very last slide. You should have learned that metamorphism is a solid state process, that metamorphism causes changes to the mineralogy of the rock and the texture of the rock. And that starts somewhere at around 100 to 150 degrees C. That's the beginning, the low temperature end of metamorphism. The high temperature end is where melting would start to happen. In a felsic rock, that would happen starting around 700, 800 degrees Celsius. If it was a mafic rock, it would start happening somewhere between 1,000 and 1,200 degrees Celsius. That's the full range of metamorphic temperatures. We've got 3 different types of metamorphism broadly. Subduction zone metamorphism with high pressures and low temperatures. I showed you the diagram where the subducting oceanic crust dragged those isotherms down with it, dragged its cool down into the depths of the earth. That's where we get blue schist and eclogite that we would find up at Ring Mountain in Tiburon. Regional metamorphism takes place in the thickened crust in continental collisions. That's sort of intermediate, medium pressure and temperatures. And then contact metamorphism, which is mostly high temperatures, and that happens in the contact aureole around plutons and other magma bodies. We talked about generalizing about metamorphic grade and just saying like low grade, high grade, intermediate grade metamorphism just describes broadly temperatures and pressures. So low grade is low temperatures and pressures. High grade is high temperatures and pressures. Um, I we looked at metamorphic facies, so like blue schist facies, eclogite facies, granulite facies, amphibolite facies. I mentioned green schist facies already. Those are the facies I'm talking about. They describe a small range of PT conditions where certain mineral assemblages are likely to exist. And I describe how green schist facies is named for some of the green minerals that grow at those conditions. Same with the blue schist facies. Blue schist facies. It's the blue amphibole that gives blue schist facies its name. We looked at some common mineral assemblages, like eclogite having green pyroxene and red garnets, and granitic gneisses having light colored bands representing the feldspars and quartz, and the dark colored bands representing the mafic minerals. Marbles and quartzites have very simple mineralogy. They've just become coarser. We talked about protoliths, so the parent rocks to the metamorphic rocks. I gave you a couple of examples of a shale, which is a sedimentary rock. That's the protolith, transforming into a slate where the foliation is developed. Then a phyllite, where micas start to grow and it develops a sheen on that foliation plane. Then a schist, where the micas or the muscovite has grown large enough to see with your naked eye, and those muscovites are laying flat within the foliation plane. So those are typical rock types that you get with increasing grade when you start out with a shale protolith. And it doesn't have to be perfectly shale. Like it could be a sandy shale, like somewhere a mixture between shale and a sandstone. There's ranges of compositions. And those are all just the ingredients that go into the metamorphic stew pot, right? Metamorphism and deformation are closely related, and you often find that metamorphic rocks are also deformed. And that deformation can come in the form of a foliation, which is a planar feature, or a lineation, which is a linear feature. And I gave you the example of like stretching in a continental rift being a place where you would see lineated rocks, or foliated rocks in a regional metamorphic environment, so in a collision belt. And oftentimes, especially if the mineralogy is working for you, you'll have both foliation and lineation. So the foliation forms perpendicular to the greatest compressive stress. The lineation forms parallel to the least compressive stress, or the stretching direction. And then we talked about naming metamorphic rocks. All foliated metamorphic rocks get the name slate, phyllite, schist, or gneiss. The non-foliated rocks get either the generic fine-grained hornfels, which is usually a contact metamorphic rock, or a granopels if it's coarse-grained, but you don't have a better name for it. You might go with granopels. But usually there's a specific metamorphic rock type that you can use. You can say a marble. That's a specific type of metamorphic rock that has a limestone protolith. You can have a quartzite. That's a specific rock type that has a quartz sandstone as a protolith. Or a serpentinite, another specific name, that is metamorphosed mantle rock. Eclogite and blue schist, the examples I gave you that were non-foliated, those were basaltic protoliths, and out of them we got those specific mineralogy at high pressures and low temperatures to give us those rock names. And then I showed you several examples of migmatites where temperature has gotten so high, the rock starts to sweat and gives off these little stringers of the quartz and feldspar that form the initial melts out of any rock. Those are the lowest temperature minerals to melt. And I refer you back to Bowen's reaction series again there, because when you move from work from the bottom up in Bowen's reaction series, that's where you'll see the minerals and the temperatures at which they would start melting. You would start with the felsic minerals, and at higher temperatures reach the mafic minerals. It works like that. It's just the inverse of the crystallization temperatures. So in terms of crystallization from a magma, you crystallize the mafic minerals first and the felsic minerals last, right? Do you see the relationship? If not, I recommend you go back and look at Bowen's reaction series in probably the first igneous rocks lecture. And just to prove to yourself that you see 700, 800 degrees Celsius for the felsic minerals, 10,000 to 1,200 degrees for the mafic minerals. And I'll call those either melting temperatures or crystallization temperatures, depending on what you're talking about. Could be melting of a metamorphic rock into a migmatite, or it could be crystallization from a melt, like crystallization from a pluton, to form an igneous rock. But we're talking about metamorphic rocks here, so. But all these processes are related, and a lot of the terminology is related. So I'm trying to bring this back in, like full circle, talk about all these different things. Hopefully it's making sense. I'm going to stop there and wish you good luck. So this will be the part 2 lecture that goes with the one I gave you on Thursday, the 5th of November. Thanks.